Okay, gang, here are the extra practice problems that we didn't get to in class. Wanted to make sure you guys knew how to do these. Quickly, on the first couple we did in class, how can you tell experimentally if a compound is ionic or covalent? Remember that if it has one of these metals on this side connected to a non-metal on this side, then it's ionic. And if it's just a non-metal connected to more non-metals, then it's covalent. Okay? You can determine this in a lab experiment by dissolving it in water, and if it conducts electricity, then it would be ionic. Number two, we kind of went over that. If it's a metal from the left here connected to a non-metal on the right, it's ionic. If it's all over here, then it's covalent. Which of the following molecules are covalent? So you're looking for the ones that don't have any metal. That would be A and D. There are no metals. Magnesium is a metal, sodium is a metal. Which of the following, number 4, are ionic? Now we're looking for metals. Right here, rubidium and sodium are metals, so these two are ionic, B and D. And number 5, okay, so I had a total brain meltdown on this one. I had forgotten that we're dealing with combustion. So let's look at this again. It'll make up for the question that I had at the end of class as to why the numbers weren't right. So in order to burn a 5.13 kilogram log, oxygen has to be added. That I wasn't even thinking. Whenever you're doing a combustion reaction, it requires oxygen, and it gets that oxygen from the air, and that needs to be added to the reactant side. If a chemist collects all these values here of how many kilograms of oxygen was needed. So let's take a look at this one. Go to the second page here. All right. So we have wood. Forgive my handwriting on this thing, it's just terrible. Plus oxygen from the air to burn creates ash plus carbon dioxide plus water. Okay, this is what needed to be remembered yesterday. Whenever you're doing a combustion, it takes oxygen from the air to create predominantly carbon dioxide and oxygen, but there's ash in this wood as well. So if we put in the numbers, the wood was 5.13 kilograms. Oxygen is what we're trying to find out. Ash, we had converted that to kilograms, which is 0.308 kilograms. We had 5.05 kilograms of carbon dioxide, and then 1.04 kilograms of oxygen. Adding all of these up over here, we have 5.13 kilograms plus over 2 is equal to 6.40 kilograms. Bring this over, leaves us O2 on this side is equal to the 6.40 kilograms minus 5.13 kilograms, and that gives us an O2 of 1.27 kilograms that was taken from the air. Okay, and there's your answer for that one. All right, let's move on to number 6. Take a look at this one here. Number 6 says, in making calcium chloride, you get 100.0 grams of calcium plus 100.0 grams of chlorine, makes 156.5 grams of product, along with some leftover calcium. That right there tells us that we use all of the chloride in this, 100% of it, so 100.0. How much chlorine and calcium should be added together to make 1,500 kilograms, 1,500 kilograms of calcium chloride without any leftovers? Sorry, I said 1,500. That's 1.500 kilograms. 1,500 grams is what it would be. All right, so let's take a look at this one. Back over here. Get a new page. All right, so let's write down what we have. We have 100.0 grams of calcium. Okay, we've got 100.0 grams of chloride. This makes 156.5 grams of calcium chloride. Okay, wow, my handwriting is terrible on here. And they want to know what we need to make 1,500 grams of calcium chloride. Okay, so to start with, we have 200.0 grams. That's what we got here, the 100 of each to start with, right? Subtract what we made, 156.5 grams of the calcium chloride, and that gives us 43.5 grams of calcium that was not used. Okay, so if we used all of this and we have 156.5 grams made, the difference on that is the 43.5. That's how much of the calcium was not used. Okay, so to find out what we did use, common sense tells us if we used 100 grams of chlorine and the total mass is 156.5, then obviously there's 56.5 grams of calcium that's not being used. We could also do that if we just subtracted the 100.0 grams of calcium minus the 43.5 grams that we did use. And that, of course, gives us 56.5 grams of calcium. So this is what we used. Okay. Now, the way I have it set up here, we're going to take a look at finding the answer using a ratio, which is going to be important doing it this way because we'll use this a lot when we get into stoichiometry. Okay. So we just set up a basic ratio. We have 56.5 grams of calcium used for 156.5 grams of calcium chloride. Okay, and that would equal X number of grams of calcium that need to be used to make 1,500 grams of calcium chloride. Okay, so this is our ratio set up. And we just do our cross multiplying and all that. We get 156.5 grams calcium chloride times X number of calcium equals 56.5 grams of calcium times 1,500 grams of calcium chloride. We're going to bring this over here, so we isolate the X. That means we get all of this. Let's do this here. 56.5 grams of calcium times 1,500 grams calcium chloride divided by 156.5 grams calcium chloride. Okay. When we do all the math here, it tells us that X is equal to 541.53 grams of calcium. And when we take our significant figures into account, which we've got 3 here, this number here goes down to 542 grams of calcium. This is how much calcium is needed. Okay? Now, to find out how much of the chloride was needed for this, we were trying to make 1,500 grams of it. We subtract our 542 grams of the calcium. Okay? And that gives us 958 grams of chlorine that are needed. Okay, so here's our answer. 542 grams of calcium and 958 grams of chlorine are needed to make our 1,500 grams of calcium chloride. Okay, now there is another way you can do this. I want you to be familiar with this way because we will use ratios a lot, like I said, when it comes to stoichiometry. However, another way we can use it, and either way is fine with me how you do this now, just understand you need to know how to do this for later on. And that is by finding a common multiple. Okay, let me move to another page here, it'll be easier to see. So, if we're doing it by finding a common multiple, then we look at where we started. We have 156.5 grams of calcium chloride. We have to multiply that by some multiple to get to our 1,500 grams of calcium chloride that we want to make. Remember, because of conservation of ratio, the word just left me. Conservation, sorry. Our conservation of ratio of elements within this mixture is going to be the same. And because of that, we can find a multiple that would bring this up to 1,500 and then use that multiple for the individual elements. So this is just basic math. We're going to bring this over and divide. So that'd be 1,500 divided by 156.5 grams. Whoops. And when we do that, our X value is equal to 9.585. Okay, this is our multiple. So if we used 100.0 grams of chloride, then if we multiply that by our multiple, which is 9.585, that gives us 958.5 grams of chloride that's needed. Okay. And then if we used 56.5 grams of calcium in our original, then we multiply that by our multiple, which is 9.585. That gives us 541.5. Spot here. And if we consider significant figures here, you've got 3. Up here you had 4 on both, so our answer could have 4. Here we only have 3 significant figures, so when we get done with this, the 541.5 becomes 542 grams of calcium. And that's how much calcium is needed. So you can see here are values that we need. Okay. We're a little off. On the other one we had 542. What did we get? 542 and 958. here we have 958.5, and that's because we're multiplying and we're using the significant figure rules for this, so it makes up for half a gram. On our original problem, we did addition, which means we go to the most precise decimal point, and it just kind of changed it a little bit. However, either way would be acceptable and correct, as long as you do the correct significant figures for it. So either way of doing the problem, you can see obviously this way here is much quicker and easier, but again, I can't stress enough, you need to know how to do those ratios, because we'll be doing that a lot in the future. All right, let's move to our next problem. Go to the page here. Number 7, it says a chemist adds 50.0 grams of nitrogen to 50.0 grams of hydrogen. This ends up making 60.7 grams of ammonia and some leftover hydrogen. What masses of nitrogen and hydrogen should be reacted to make 150.0 grams of ammonia with no leftovers? Okay, so let's write down what we know first. Okay, we know that we have 50.0 grams of nitrogen. Okay, we know that we have 50.0 grams of hydrogen. We also know that that made 60.7 grams of ammonia. We also know that we have extra hydrogen. We didn't use all the hydrogen. Okay? And then the question is, what do we need to make 150.0 grams of ammonia? Okay, so again, I'll do both ways. Again, we'll start with the ratio, and then we'll do finding the common multiple. Okay, all right, so common sense here first. Let's look at this. It says we have excess hydrogen. That means we're not using all 50 grams of hydrogen. That also means we are using all of the nitrogen. If we have 60.7 grams that were made, common sense tells us 50 grams of that is the nitrogen. That means whatever the leftover is going to be the hydrogen. And the leftover would be 10.7 grams. Okay? So that tells us that we used, I'm going to put it over here, we used 10.7 grams of hydrogen. Whoops, went off the top of the page, sorry. There we go. Rewrite that so it's on the page, you can see it. Okay, so we used, okay, that's it, not going back to my pen. There we go. This is how much we used. So if we're doing our ratio, then we know that 10.7 grams of hydrogen is used for every 60.7 grams of ammonia. That means that how many grams of hydrogen are needed to make 150.0 grams of ammonia. Okay. Again, cross multiply, find our answer. We get 60.7 grams of ammonia times X is equal to 10.7 grams hydrogen times 150.0 grams of ammonia. It's supposed to be a 3. That's terrible. There we go. Oh, this is terrible writing. Sorry. Okay. Isolating this X on this side using basic math, that gives us 10.7 grams of hydrogen times 150.0 grams of NH3. All of that is divided by 16.7 grams of ammonia. Do your math here, that gives us 26.4 grams of hydrogen that was used. Okay. Now, they wanted to know if we made 150 grams of ammonia, how much of each product. We just discovered that we used 26.4 grams of hydrogen, so we subtract that from our 150.0 grams, and that gives us 123.6 grams of nitrogen used. There are two values, 26.4 grams of hydrogen and 123.6 grams of nitrogen. Okay, so let me get another page and we will use the common multiple to find the same answer. Okay, so we have 60.7 grams of ammonia times some multiple to get to 150.0 grams of ammonia. Okay, do our math, isolate, we have 150.0 grams ammonia divided by 60.7 grams ammonia. That's how the ammonia cancels out as well as the grams. And this gives us an answer of 2.47. This is our multiple. Okay. We're going to multiply our element values from the first reaction by that to get us to our 150. So we know that we used 10.7 grams of hydrogen. So we multiply that by our multiple of 2.47. That gives us 26.4 grams of hydrogen needed. Okay. We also used, at the beginning, 50.0 grams of nitrogen. Multiply that by our multiple, 2.47. That gives us 123.5 grams of nitrogen. You see our sig figs here, we have 3 as our greatest number of significant figures, which means this 5 is going to cause that 3 to become a 4. So that gives us 124 grams nitrogen needed. Okay. So there we go. The 26.4, 124, add together, gives us close to our 150 that we needed to make. Okay? All right. Let's look at number 8. Get a new page here. Number 8, it says, if you were to react 120 grams of carbon with 4 grams of hydrogen, excuse me, let's read that correctly. If you react 12.0 grams of carbon with 4.00 grams of hydrogen, you'll make methane with no leftover, so you use all of both. If a chemist reacts 150 grams of carbon with 150 grams of hydrogen, how many grams of which element will be left over after the methane is made? All right, so let's put down our data and then we'll talk about this one. Okay. We have 12.0 grams of carbon. Okay. We have 4.00 grams of hydrogen. Okay. We used all of this. Okay. They want to know if we mix 150.0 grams of carbon with 150.0 grams of hydrogen, they want to know how much of which is left over. Let's go back to the question, make sure. Whoops. Oh, good cord. There we go. All right. So you have 150 of each. How many grams of which element will be left over? That's what they're asking. How many grams of which? So common sense, first of all, let's look up here. We have 12.0 grams and 4.00 grams, okay, of hydrogen. All of this is used, okay? We come down, we see here that it takes more carbon than it does hydrogen in grams to make this mixture react the way it's supposed to. So if we use that common sense-wise down here, we're going to use more of the carbon than we will of the hydrogen in this mixture as well, right? So that means that we will end up using all of the carbon and some of this hydrogen. So right off the bat, we know that what's going to be in excess when we're done is going to be the hydrogen. Now we just need to figure out how much, okay? So again, we could do this using ratios. So let's take a look at what we have here. This is a little different because they don't tell us our end value. We're just doing the ratio of hydrogen to carbon in this reaction. And then we're going to look at that same ratio of hydrogen to carbon when the carbon is 150, because we do know that. So let's write this down. We have 4.00 grams of hydrogen that's being used for every 12.0 grams of carbon. And our new ratio, we want to know how many grams of hydrogen for every 150.0 grams of carbon. Okay, so there's our ratio. Again, same thing, isolate. We've got 12.0 grams of carbon times X amount of hydrogen equals 4.00 grams of hydrogen times 150.0 grams of carbon. Isolate our X value. That gives us 4.00 grams of hydrogen times 150.0 grams of carbon, all divided by 12.0 grams of carbon. Okay, do our math. That gives us 50.0 grams of hydrogen that's being used. So of the 150 hydrogen we were given, we only use 50 of it. Well, if we only use 50, how much is left over? 100. So that one should be pretty easy, right? We've got 100 12.0 grams of hydrogen left over. Okay, here's our answer. That's, again, using ratios. We can solve this using multiples as well. So let's go to a new page here and we'll solve it using multiples. So we have 12.0 grams of carbon times what multiple will bring us to 150.0 grams of carbon. You notice how we're doing it based on the carbon and not on the total amount of product, because we initially don't know how much product it's going to make. They just gave us how much of each we want to use. Okay, but same idea. We do this. We isolate our x value, 150.0 grams of carbon, divided by 12.0 grams of carbon. That gives us our multiple of 12.5. This is what we're going to multiply our initial amounts of carbon and hydrogen by. So initially we had 12.0 grams of carbon. We should know this one already because we just did it in the opposite to find it. So we know this will give us 150.0 grams of carbon used, which is what we used common sense to say was going to be used in the first place, all of it. The one we didn't know was the hydrogen. We had 4.00 grams of hydrogen in our first reaction. Multiply that by our multiple, 12.5. That gives us 50 grams of hydrogen used. Okay, we have three significant figures, so that would actually be 50.0 grams. Let me rewrite that so it doesn't look so ugly. Back to my pen. There we go. So that's 50.0 grams. There we go. Of hydrogen used. Okay. So you see, we got the same answer doing the ratio or the multiple. This, I mean, it looks like it's a little bit less math, not much, but either way works. Whether you're finding a common multiple to increase, since we know the law of definite proportions says that those proportions will be the same regardless of how much we use, or you can do it finding the ratio, which does the same thing. Okay? All right, that's question 8. Let's look at question 9. Question 9 says, in making aluminum sulfide, 54.0 grams of aluminum and 100.0 grams of sulfur make 150.3 grams of aluminum sulfide and leftover sulfur. So again, right away, we know we're using all of the aluminum and some of the sulfur. How much aluminum and sulfur should be used to make 150 grams of aluminum sulfide with no leftovers? Okay, this is just like we did with the other problems. So let's get a new page here, and we will take a look at this. Let's write down what we have. Okay, we know that we have 54.0 grams of aluminum. Okay. We also know that we have 100.0 grams of sulfur. And this makes 150.3 grams of aluminum sulfide. Don't worry about the written molecule. I'm just doing it because it's easier than writing out aluminum sulfide. We'll learn how to make these formulas in the future. Okay. We also know that we will have excess sulfur. We don't use all the sulfur. And they want to know how much is needed to make 150.0 grams of aluminum sulfide. Now, what's the first thing you notice here? Our initial sample, we made 150.3 grams of aluminum sulfide. If you notice, in our final answer, they want to know what's needed to make 150.0 grams. That is a tiny difference, 3/10 difference. It's also less than what we started with. That doesn't matter. Because of the law of definite proportions, we could still use our ratio or the multiples to get the correct value of reactants needed. Okay, we have everything here that we need. So let's start with the ratio. Okay, we have 150.3 grams of aluminum sulfide. We know that we used 54.0 grams of aluminum, all the aluminum. When we subtract that, it tells us that we used 96.3 grams of sulfur, okay, for this first reaction. 96.3. This is what we're going to use in our ratio. So if we used 96.3 grams of sulfur to make 150.3 grams of aluminum sulfide, then how much sulfur will be needed to make 150.0 grams of aluminum sulfide? Okay, same thing, cross multiply, 150.3 grams of aluminum sulfide times X number of sulfur equals 96.3 grams of sulfur times 150.0 grams of aluminum sulfide. Okay, finish our math. 96.3 grams of sulfur times 150.0 grams aluminum sulfide divided by 150.3 grams of aluminum sulfide. Finally get our calculator out, do all this, it comes up to 96.1 grams of sulfur is used. In the new one. So we initially used 96.3, right? And our new mixture, it's going to be less than our initial one. So how much we use should be less, which it is, 96.1. Not much, but it is less. And with that, we know that we had 150.0 grams of aluminum sulfide. Subtract our 96.1 grams of sulfur that we know we used because of our ratio. That tells us that we have 53.9 grams of aluminum that's used. Okay, so there's our two values, 96.1 and 53.9. And notice both of them are less than what we started with up here, which should make sense, and not much less because we're only a small, 3/10 off from our original. All right, so let's take a look at this using multiples. You'll see that it works out the same way. Let's get a new page here. Okay. All right, so using multiples, we have 100 150.3 grams. That's where we're starting. Our final amount that we made, right? Times some multiple to get to 150.0 grams of aluminum sulfide. Where we started and where we want to end. Remember, it's less in this one. Okay, we just do our math. That gives us 150.0 grams aluminum sulfide divided by 150.3 grams of aluminum sulfide. Our multiple comes out to 0.9980. Okay, so this is what we use with our original values that we started with. If you remember, we found out, or from the beginning, that we used 96.3 grams of sulfur, and we used 54.0 grams of aluminum. So we multiply both of these by our multiple. This one comes up with 96.1 grams of sulfur needed. And this one times our multiple comes up with 53.9 grams of aluminum needed. Okay, and there are our same values we got using the ratio. Okay, same thing whether you do the multiple or the ratio. Okay, all right. I think we've looked at the rest of the problems in class. Let's look at number 10. Give a chemical formula for each of the following compounds. Okay, here we have diphosphorus hexaoxide. Remember, di means 2 and hexa means 6. So when we write this, we get phosphorus had 2, oxygen had 6. Diphosphate hexaoxide. Okay. And for B, we have dinitrogen tetrahydride. Let me move this over here. Look. Both of them at the same time. There we go. All right. So on our next one, we have dinitrogen, 2 nitrogen. So for B, we have 2 nitrogen and tetrahydride, 4 hydrogen. There you go, and 2 H4. And for C, we have nitrogen monoxide. Nitrogen, there's nothing in the front, so that means that there's only 1 nitrogen. And mono meaning 1 oxygen, NO, nitrogen monoxide. Okay. All right, so number 11. Whoops, let's go down a little lower. Number 11. It says give the names of the following compounds. So here we've got SO2. S, when we go to the periodic table, sulfur. O is oxygen. So we have sulfur, which we know is a nonmetal on the right-hand side of the periodic table. Let's take a look here. Oops. Sulfur is right here. Oxygen is its upstairs neighbor. They're both nonmetals. Both being nonmetals means that it's covalent, so you need to follow the rules for writing covalent, which means you have the prefixes. There's 1 sulfur, so it's just sulfur. Okay, and then where am I here? The other is oxygen, and we have 2 of those, so it's dioxide. Change your ending of oxygen to IDE. Sulfur dioxide. That's for A. Okay. All right. So B, we've got CaCl2, calcium and chloride. When we go to our periodic table, you see calcium is in our second column right here. That's definitely on the metal side. And chlorine is way over here, definitely in the non-metal. So it's a metal and a non-metal. When you have metal and non-metal, that means that you're dealing with ionic. Ionic means that you use the first element, which in this case is calcium, and then you use the second name and change the ending of it to IDE. Calcium chloride. Okay. All right. So for our next one, we have C. On C, it is NaS, Na2S. Na is way over here in the left-hand column, so that is a metal. And S is way over here on the right, sulfur as a non-metal. So metal and a non-metal tells you it's ionic. So you can use the first name, and then the second one you change the ending to IDE. Okay. Oh, wait a minute. Did I do the wrong one? Calcium. Oh, I skipped C. Whoops. All right, so this is D. We'll go back to C here in a second. And let's change this to D. All right. So D is sodium and A, we said. So that's sodium. Oh, it's terrible. And the second one is sulfur, so that becomes sulfide. Change the ending to IDE. Sodium sulfide. Let's go back to C, since I wrote the wrong thing down here. Okay, on C, we have oxygen and chlorine. They're both non-metals, so we have the prefixes. This is oxygen. There's only one. We don't have to use mono in that case. And the chlorine, we have 2. And the prefix for 2 is di. And then we change the ending to IDE. And that gives us oxygen dichloride. Okay? All right. Last one down here, number 12. Classify each of the following elements, compounds, homogeneous, mixture, or heterogeneous. A bowl of milk in cereal. Here you've got all of your elements that can be separated here very easily. You can take a spoon to take the cereal out of the milk. That makes it a heterogeneous mixture. Okay, and then B, we've got a bottle of H2SO4. This is all H2SO4 in the bottle, so that would be considered our compound, all the same. And then C, copper wire. It's all copper. Copper is right here on the periodic table, Cu. And then since it's all copper, that would be our element. And then D, Kool-Aid, dissolved in water. That's not very easily separated, and it's evenly mixed throughout, so that would be our homogeneous mixture. Okay? All right, there's your problems. I hope that helps, since we didn't do all those in class, and I will see you on Tuesday. If you have any questions, please email me, and I'll be glad to help.